Well, thanks for having me. I'm happy to be here on this snowy evening. So just to note, when I'm in this presenter mode, I can't see the chat. So if you have a question that is really pressing, then just, if you're muted, you can unmute yourself and ask. If you're not muted, go ahead and ask as I go along. Or I'm also happy to take questions at the end, whatever you prefer. I'm flexible. Okay, so as you heard, I'm a professor at McMaster University. So I've been in Hamilton for about a dozen years, for a couple of years in Germany. So I lived in Munich, Germany. And before that, I did my PhD also in Ontario at the University of Waterloo. So I've been in Ontario off and on a lot in the last couple decades. My research is in galaxies primarily, which is what I'm going to talk about today, and also dark matter. So if you have pressing questions about cosmology, I'm also happy to take questions on that, even though it's not what I'm going to present tonight. Okay, so I'm an observer. So the talk today is not going to be on theoretical astronomy. It's going to be much more observationally based. And what today I want to do is talk basically about some shapes and some basic properties of galaxies. And then I'm going to talk specifically and show lots of images of interactions between galaxies. And in the second part, I will focus on how galaxies and their properties depend on the environment in which we find them. So what I mean by that is that galaxies live in a wide variety of places in the universe. Sometimes they're pretty lonely and live by themselves, and sometimes galaxies have lots of nearby neighbors, and their evolution actually depends on which of those situations we're in. So do they have lots of neighbors or do they not? So you can't give a talk on galaxies without showing lots of pretty pictures. So here are just a few beautiful, mostly, I guess in this case, Hubble Space Telescope images of some amazingly beautiful galaxies. Some of them show features that we're going to hear about tonight. So on the left, the big one, actually, let me see if I can get my laser pointer going here. Okay, so here, this is actually an interacting pair of galaxies on the left. And some of these big features you see are material actually being stripped out of galaxies as they gravitationally interact. On the upper right, we have a fuzzy, big, faint disk around a galaxy. And on the bottom right, we have a very different kind of galaxy than the others. This is an elliptical. So galaxies come in two basic shapes, as we're going to see: spiral galaxies, which are the ones we all like to take pictures of, and then big red blobs, which don't show a lot of features, but are interesting because they are the end point of galaxy evolution. If you merge together and smash together a bunch of things that look like the ones on the left, you end up with a galaxy that looks like the one on the right, a big red kind of featureless blob, as we're going to see. So one other important piece to note as we look at all the pictures of galaxies today is that when we see galaxies, we're only seeing the visible part. So the part of the galaxy that we can see gives off light. And so that's made up of stars and gas and dust and things that we can detect at different wavelengths of light. But that's only a small fraction of what a galaxy is. Most of the mass of a galaxy is in something called dark matter. So again, not what we're going to talk about today, but I want you to rethink your picture of what a galaxy looks like. So you see a beautiful galaxy like this. That's the visible part you can see with your telescope. You can take nice images of, but that lives in a much larger, much more massive structure called a dark matter halo. And why it's, yep, go ahead.
At the last meeting, we talked about 2 meetings ago, actually, we talked about globular clusters. Does the dark matter extend out to the globular clusters or beyond it, according to current theory?
It's not just theory, it's measurement and beyond. So the globular clusters orbit around the main galaxy in the dark matter halo, but the dark matter goes out even further than these star clusters that we can see. But these globular clusters, their orbits can actually tell us how much dark matter is there, which is kind of amazing.
Thank you.
Yeah. So yeah, this is not just a theoretical picture. This is actually something we can measure. We can measure it by studying, of course, we don't see dark matter, but we see the gravitational impact of dark matter on galaxies in the universe. So if I'm going to show you pretty pictures of galaxies tonight and talk about all this stuff we can see, why am I mentioning dark matter? It's because it is most of the mass of a galaxy, and therefore it is the most important gravitational component. So when you take two galaxies and you ask, why are they interacting? They're interacting because they feel a huge gravitational pull because they have so much dark matter. If the dark matter wasn't there, these two galaxies might not be interacting as strongly. So the gravity is dominated by all this dark matter that has tons of mass, tons of gravity that we don't see.
Laura, Laura. Oops. I just want to finish an idea. How do globular clusters help us probe dark matter again? Can you give us an example?
Yeah, so anything in nature which is in an orbit. So let's take, for example, the Earth is in orbit around the sun. Using the properties of the orbit of the Earth, we can estimate how massive the sun is. So in our own galaxy, imagine the main part of the Milky Way where we live in the disk of the Milky Way, how fast the sun orbits around the center of the Milky Way can tell us how massive the Milky Way is, but only the part between where we live and the center of the galaxy. So this is a law of nature that you're only sensitive in your orbit to the mass between the center of the object and you. So the Earth can tell us about the mass of the inner solar system, but not the mass of the outer solar system. The sun's orbit can tell us about the mass between us and the middle of the Milky Way. Why globular clusters are so powerful and so important is they exist way out here, beyond where most of the stars and the gas in the Milky Way live. And so that means they're tracers of all this mass out here between their location and the center of our galaxy. Does that help?
Yes.
Great. Was there another question there?
I was going to mention a couple of weeks ago, I read an article and it was talking about the halo that surrounds Andromeda and how the Milky Way was already within the vicinity of the halo that surrounds Andromeda. Safe to say those two galaxies are already interacting with one another, even though they appear to be still so far apart?
Yeah, so our dark matter halos are if they're overlapping, it's only out at the very, very, very edge. So we're not strongly interacting yet, but give it a billion years and it's going to be pretty dramatic. So the final collision of these two galaxies is about 3 or 4 billion years in the future, but we're getting closer every day.
I'll mark my calendar.
Yeah. Okay. So today I'm going to talk about galaxy evolution. And of course, what I mean by evolution is not like biological evolution, but just change that happens over time. And as an observational astronomer, one of the most frustrating things is that I study something that you cannot directly observe. And why is that? It's because galaxy evolution is a complicated combination of a bunch of processes, all of which happen over timescales, which are at least millions of years, but more typically billions of years. So I cannot go take an image of a galaxy and then go take an image the next year and the year after that and see any change. The time scale of my lifetime is nothing on the time scale of galaxies. So we can't see individual galaxies evolve. So how do I actually know that galaxies change over time? How do we study that observationally? And there are two main approaches. One is what I would call something akin to archaeology. So that's where you can look around us nearby, like look at the Milky Way, look at nearby galaxies, and look at very old things, including things like globular clusters, which formed a really long time ago, and study their chemistry and the detailed properties to try to understand the past. How did they get to be the way they are? So that's one way to study galaxy evolution. And the other is to look out at distant galaxies and see how populations of galaxies have changed over time. So again, I can't see one galaxy change, but I can study galaxies 1 billion years ago, 2 billion years ago, 3 billion years ago, and see how on average galaxies have evolved. And so just a reminder here about the fact that when we look out at distant objects, when we see galaxies that are millions of light years away, we're seeing what they looked like in the past. And with the work I do, I'm usually studying galaxies that are billions of light years away. And so I study them at an earlier epoch in the universe, and I can see what galaxies looked like in the past. And then we can try to figure out what are the processes that are changing them over time. So this is perhaps a familiar diagram to some. This is called the Hubble tuning fork diagram. So Edwin Hubble, famous observational astronomer who did work starting now over a century ago. Some of his important work was published around 1920, so really a century ago. And at the time that Edwin Hubble was doing observations, there was, at the early part in his career, there was even a debate about whether galaxies were external to the Milky Way or fuzzy nebulae within our own Milky Way. But as we've come to learn, galaxies, we live in one called the Milky Way, and there are billions of other galaxies out there. But one of the things that Edwin Hubble did that has survived is this way of classifying the shapes or the morphologies of galaxies. So this tuning fork diagram in Hubble's day was perhaps, some people thought it was an evolutionary sequence, that galaxies move from the left to the right. We now know that's not true, but it's still a useful tool for categorizing the shapes of galaxies. So what you have on the left are the class of galaxies called ellipticals. These are big, almost featureless, orangey red blobs, and they're very three-dimensional. And so the average orbit of a star is, each star has its own orbit, and it's like a swarm of bees around the center of the galaxy. And that's in contrast to the galaxies on the right, which are more like the Milky Way. These are spiral galaxies, and I picture them like a frisbee. So they are very thin if you look at spiral galaxies edge on, and big if you look at them face on. And the stars in the galaxies orbit around the center. And so very ordered rotation of the stars around the center of the galaxy, unlike the ellipticals on the left where we've got random orbits. But it's not just the shape of galaxies that is different along this diagram. Also, we now know that the galaxies on the right, the spiral galaxies, some of which have bars, the ones on the bottom, some which don't, the ones on the top. These galaxies on the right have a lot of star formation. They have a lot of gas. They have bluish colors, and that's coming from hot young stars. The galaxies on the left are dominated by older stars, no hot, young, recently formed stars. So they don't look blue. They have very little gas. So they have fundamentally different properties. And so one of the big questions in galaxy evolution research is, why do we have this diversity of galaxy properties, and how do they evolve over the history of the universe? So that's one of the things we study in my research group. So a really brief reason why you might have these two kinds. So why spirals and ellipticals, these kind of two classes of galaxies. And I've left out on the right here, the ones that don't fit in. So we've got lots of irregular galaxies, which don't fit in, but most galaxies are one of these two categories. And the number one reason why you might have one shape versus the other, three-dimensional blob versus a rotating disk, has to do with what happened at the time the galaxies formed. So galaxies form at different times in the history of the universe, but they basically form by gravity winning out. You've got some chunk of material in the universe, dark matter, gas, dust. And when there's enough material in a small enough volume, if gravity wins out, that material will collapse. And if, as the material collapses, if it has a lot of what's called angular momentum, or you can think about it as a little bit of spin, as it collapses, it will spin faster and faster and faster and faster, and it will naturally make a disk. So this is kind of like a figure skater pulling in their arms, they spin faster and faster. If you take an initial cloud, if it has any rotation at all, as it collapses, it's gonna spin faster and faster. So an initial cloud that has a bit of rotation you'll end up with a frisbee-like galaxy. An initial cloud that collapses that doesn't have rotation, so maybe it had nothing nearby to give it torques and it was just a blob of material that collapsed, it can collapse into something that looks quite spherical. So that's one reason why you would have an elliptical versus a spiral. But then galaxies don't just form and stay the same forever. Our universe is filled with interactions between galaxies. And so galaxies can merge with each other to make bigger galaxies over time. You can have other interactions that are not mergers. So you can actually transform yourself from one galaxy to another depending on these interactions. So formation matters, but also interactions with your neighbors, which we're going to talk a lot about tonight. So just another picture here to show you kind of a view of a spiral face on versus an elliptical. And in one case, the stars are orbiting in nice circular motion, and in the other, they're all on random orbits. And if you take something where everything's in nice ordered rotation, and you smash two of those things together where everything's nicely rotating, you randomize all the orbits, and you naturally end up with an elliptical galaxy. So take two spirals like the Milky Way and Andromeda, smash them together, and you will get something that looks like an elliptical.
Excuse me, Laura, can I ask you something else?
Yeah, of course.
So based on this, it means that ellipticals have a lot of gas too, just like the spirals.
They don't. And so the reason for that is during the merger, which I'm going to show you a picture of in a second, at the moment that two galaxies that have a lot of gas interact, that gas gets funneled to the center of the merging system and forms a ton of stars in what's called a starburst. And it uses up all the gas. So in principle, you're right. You start out with two gas-rich galaxies. It all ends up in the final galaxy. It's just that it gets used up really quickly. So when the two galaxies smash together, a huge burst of star formation uses up most of the available gas. So you're left over with this object with very little gas in it.
Okay.
I have a question.
Sure.
Okay, you said that when two spiral galaxies collide, they will form an elliptical. Does it only take two spiral galaxies, or does it take interactions of more than of several galaxies over time to promote the formation of an elliptical galaxy? I would think it would take more than just two two galaxies merging to promote the formation of an elliptical galaxy.
So if you have what we call a major merger, so two kind of similarly massive big spiral galaxies, and you smash them together, they will make an elliptical.
Oh, really? So like
all of those, Andromeda and the Milky Way, when we're all done, we're gonna be living. So if you're all around in 5 billion years, we are going to be living in an elliptical shaped galaxy.
Oh, wow. Okay.
Yeah. But you're absolutely right that you don't have to only have two galaxies interact. And in fact, when the universe was younger, it was smaller. We've been expanding for billions of years. So the whole universe was quite a bit smaller in the past. And galaxies interacted even more than they do today. And so we think there were oftentimes mergers that were not just two galaxies, but lots of galaxies merging together. So it doesn't have to be two, but two is enough to make an elliptical.
Okay. Thank you.
Dr. Parker?
Yeah.
I don't want to get too far off the track. Would you care to make a comment on what an irregular galaxy is? Could you make a comment on that?
So an irregular galaxy is one that doesn't fit this nice classification scheme of a spiral or an elliptical. And I would say most irregular galaxies fall into one of two categories. They are either galaxies being captured at the moment of a merger, so they look like a train wreck, because you capture the galaxies, you take a picture at the moment where they're interacting strongly, you get a mess. Or they are little tiny galaxies, which we call dwarf galaxies, much less massive than the Milky Way. And small galaxies can very easily be disrupted by neighbors in all different ways. And so little galaxies are very susceptible. I'm going to show you some stuff later about the effect of living in a rich environment with lots of neighbors. Dwarf galaxies can be kind of destroyed by their neighbors. And so we often categorize those as irregular.
Thank you.
Yeah. Okay. So I've just said this, but just a reminder, galaxies live in dark matter halos. So what's actually happening is you're taking two galaxies in two dark matter halos, merging into one. The two galaxies, let's say they're two nice spirals, they will merge into making an elliptical at the end. So of course, you don't have to just merge spirals. What happens if you merge ellipticals? Well, you already have things that are three-dimensional blobs. You take two three-dimensional blobs and merge them together, you make a bigger three-dimensional blob. So mergers of all different kinds of galaxies can happen. And the end product tends to be things that are less disky, less Frisbee-like, and more three-dimensional as you smash things together. Now, of course, the universe is complicated. And so I'll add one note here just out of interest. If this happened a long time ago in one system, let's imagine there was a Milky Way and Andromeda, similar galaxies, but 5 billion years ago. They merged, they made an elliptical. If you leave an elliptical alone in the universe for a long time in some corner of the universe, it can actually accrete new gas from the cosmos, from large scales beyond the galaxy. There's gas out there. It can actually accrete new gas. And if it has angular momentum, it will spin and it can make a new disk. So although if you smash two disk galaxies together, you make an elliptical, left alone in the universe for long enough, that elliptical can grow a spiral around it, which is kind of neat. Okay. A point of what happens during these collisions when galaxies collide. So here's an example of something that if you took a picture of this with a telescope from the ground, you would say, oh, I have a very weird looking object. This is an irregular galaxy. When you point the Hubble Space Telescope at it with the much, much, much better spatial resolution we can get from space, then you see this is actually multiple galaxies merging together. It's a complicated mess. It's irregular, but it's not one object. It's multiple objects merging. There's a really important physical concept to understand about when galaxies merge. So let's remember what a galaxy is. It's stars and gas and dust living in a big dark matter halo. And stars and dark matter are material that we call collisionless. So what does that mean? If I take two galaxies and smash them together, galaxies are made up of stars, gas, and dark matter. The stars and the dark matter, you can think of them as being, the stars are particles, individual stars. We think that dark matter is also some kind of particle. The distance between all those particles is so big that when you smash them together, the stars and the dark matter don't collide. They just kind of pass through each other. So picture, our sun. The nearest star is 4 light years away. So if we collide our galaxy with another galaxy, the chance of the sun colliding directly with another star is negligibly small. The distances between stars are huge compared to the sizes of stars. So star particles and dark matter are collisionless. They just pass by each other. Gas is like clouds we have in the sky, right? Gas clouds like to collide with each other. You push one cloud into another cloud, they don't just pass by each other. They interact, and they interact strongly. So during a collision, the merger of galaxies, the gas collides. When you compactify gas, when you make it denser, that's one of the things that can trigger star formation. So going back to an earlier question, when you smash together two galaxies that have lots of gas, the gas collides, interacts strongly, and forms a whole bunch of stars. And then the gas is used up. So you're left with an end product. The dark matter and the star particles pass by each other, but if they're gravitationally bound, eventually they'll settle down into this 3-dimensional blob, and the gas will have been used up, making some stars. And then over time, those stars will fade to being red and dead stars, and there's no new star formation. Okay. And some beautiful examples because, of course. So here's a famous pair of interacting galaxies. These are merging, and there's been some nice HST imaging of the central part. So these are the antennae galaxies. So we see here a composite of Hubble optical imaging combined with infrared imaging from the Spitzer Space Telescope and X-ray, so very energetic light coming from really hot sources from the Chandra X-ray Observatory. And this makes the multicolor view that you see here. So when you smash together two galaxies, the nuclei of the galaxies, you've also got these huge tails we can see extending out to very large distances. But where the two central bits are merging here, we have a huge burst of star formation enshrouded in dust. So it's glowing in the infrared, which we can see. These hot sources being formed, these X-ray sources we can see. Lots and lots of star formation happen when you smash together two galaxies. So this is one famous example. This is another one that's in process right now, the MICE. This is again a Hubble Space Telescope image. This is one that has been nicely simulated. So this is a simulation which was done by John Dubinsky at the University of Toronto, showing a merger that was set up to reproduce what the MICE system looks like. So here you're seeing in the simulation the star particles. There is dark matter and gas in the simulation. They're just not visualized here. We're just seeing the stars. So this is what's lovely about doing simulations. You can see galaxies evolve. As an observer, we get one snapshot in time. In a simulation, you can see the evolution. So this was set up to have two galaxies with the same mass, the same amount of stars, et cetera, as the MICE. And then you can see the merger proceed, and you see the positions of the stars, but the color is also important. So the color is meaningful here. And it's not going to settle down into looking like a smooth elliptical, but let's imagine instead of having a perfect resolution, you looked at this with a fuzzy ground-based telescope. This would start to look like a three-dimensional blob by the end of this simulation. And if you let it go a couple more billion years, all of these features would fade and you would just have an elliptical galaxy that looked orangey red to us. So if you Google John Dubinsky, he has a website with some other views of these kinds of mergers. And he's also put on even performances where they're set to classical music, which is quite nice, smashing together of galaxies.
So this video simulation, it represents how many billions of years?
Oh, that's a good question. This is probably about a 2 to 3 billion year total time snapshot from the beginning to the end.
That's all. Okay. Wow.
Yeah. So a merger from the first approach to settling down is on the order, which is a physicist's favorite way of saying, I don't know precisely, but about 2 billion years.
Okay. Thank you.
Yeah. Okay. And just to note, interacting galaxies are not rare. So it's not like we're studying some uncommon thing that doesn't happen very often. The universe is filled with interacting galaxies. And here's just a few of the collection of galaxies that have been observed by the Hubble Space Telescope. All different stages of their merger. Some of them are on first approach, some of them have almost merged together into their final galaxy, but we have lots and lots of interacting galaxies. And so as observers, we have this problem where we only ever see one snapshot, unlike the nice simulation. Of course, the simulation is only as good as what you put into it. So if you don't understand 100% of the physics that happens in galaxy evolution, your simulation's only as good as what you've put in, but you can actually see one system evolve. We can't see a system evolve observationally, but we can study many systems at all different phases in their merger and try to understand what happens at each stage. And just to note, at the end of the day, after two galaxies like the Milky Way and Andromeda have combined together, you do get a three-dimensional blob, but for a long time, you can have these faint features that can last for a while. Ripples, shells, even sometimes multiple cores down in the center. If anyone's been following the exciting research on gravitational waves detected from black holes, the holy grail for the next generation of gravitational wave detectors is to try to find two supermassive black holes merging in a galaxy as two galaxies finally coalesce into one. We haven't found that yet, but that's the goal. Two supermassive black holes merging. So you have to wait a long time for these remnants of the merger to totally disappear. But also to see these things, you need really, really deep imaging. It's not easy to find these faint features, but they are there if you look carefully. And we've talked about the Milky Way and Andromeda, so I thought it might be fun to show this simulated view of what our night sky will look like in the future. So here we are today, where you have some horizons, some skyline here, and we have the Milky Way. Andromeda, those of you who have spent a lot of time looking at the night sky, you know what Andromeda looks like today. So this is exaggerated, so you can see it here. This is what it will look like if you wait, probably 500 million years or so. And then this is what our night sky will look like during the merger process. And then at the end of the day, in 4 billion years or so, when we're living deep inside an elliptical galaxy, our night sky is actually going to be a lot brighter. And we're going to have a higher density of stars around us, but they're going to be mostly orangey red stars. And so the sky is going to look like this. And I have to say, this is pretty depressing for an observational astronomer, because living in a Frisbee is really, really convenient if you want to study the faraway universe. Just don't look along the Frisbee. Don't look within the Milky Way. Look above or below, and you can see the distant universe. When you're living inside a three-dimensional galaxy that's bright in all directions, you have a much harder time seeing the faint distant sky and faraway galaxies. So I'm happy I live at this time to do observational astronomy and not this time. This would be a lot harder. This is like serious light pollution from all those annoying Milky Way stars. Okay, and I mentioned this earlier, but the universe has evolved over time to be much, today it's much more rarefied. Everything is more spread out than it was in the past. So if we use telescopes to look at really, really, really distant parts of the universe by having extremely long exposures, like 20-day exposures on the Hubble Space Telescope, you can start to find objects that look like this. This one's called the Spiderweb Galaxy, and this is a merger happening with, I don't know if you can even count them, but 10-ish dwarf small galaxies all at once undergoing one big merger, all kind of combining together to make a bigger galaxy. So in the early universe, mergers between many galaxies were much more common than they are today, just because everything was closer together when the universe was smaller. Okay, so we talked so far about like big mergers between what we call major mergers between like the Milky Way and Andromeda, but that happens and we're about to experience this. But those major mergers where you have two galaxies of comparable mass are less common than what we would call a minor merger, where you have a huge galaxy, here like famous nearby galaxy, M51, and a smaller companion. And so these kind of mergers or interactions are much more common in the universe. And the final end product is not so easy to predict. It depends on what the mass ratio is between the two of them, what their relative orbit is. There's a lot of things that go into determining what the final end product is. But often what happens is the little galaxy gets destroyed. And so sometimes you hear the phrase galactic cannibalism. And that's when a big galaxy eats a little galaxy. And over time, all evidence of the little galaxy disappears. And again, this happens often too. It's happening right now in our own Milky Way. So here's a side-on view of the Milky Way in this projection. So the Milky Way, the disk of the Milky Way runs across the middle. And if you've ever had the opportunity to go to the Southern Hemisphere, you may have seen the Large and Small Magellanic Clouds. So these are the two largest dwarf galaxies that are in orbit around the Milky Way, two of our satellites. They are being shredded as they orbit around the Milky Way. So we think the latest research on this, the best understanding we have of the system is these galaxies have fallen in pretty recently. So they're on their first infall, their first orbit around the Milky Way. And as they orbit around the Milky Way through this dense dark matter halo that we have, their stars and their gas is being stripped out behind them. And actually material from the Small and Large Magellanic Cloud is stretched out over a huge fraction of the sky. So this is called the Magellanic Stream. So this is eventually what we would call a minor merger. Over time, the Large and Small Magellanic Clouds are just going to get more and more shredded by the Milky Way until the evidence of their existence will start to disappear. And that's not the only one of these things in our night sky. We also have the Sagittarius Stream, which was a dwarf galaxy shredded by the Milky Way. And there's others labeled here too, Orphan Stream, Monoceros Stream. So we have destroyed a bunch of dwarf galaxies that have dared to come close to us. And this happens all the time. Another beautiful example here of an edge-on spiral galaxy and a dwarf galaxy that over an orbiter or two has just left behind all of its stars. They've just been stripped out of the dwarf galaxy and have been left in orbit around the host.
Curious as to if there is a black hole at the center of all galaxies, what happens to the black hole from those dwarf galaxies when they are cannibalized, so to speak?
Yeah, so there is a supermassive black hole at the center of all massive galaxies. For dwarf galaxies, the evidence is not so clear. So for very low mass galaxies, they probably have a dense cluster of stars in their center, but not a black hole. But it's an excellent question. A black hole is not special unless you get super, super, super close to it. So all the weird gravitational things that we like to think about are not really relevant most of the time. A black hole is just like, it orbits, if there's gravity, just like any old star. It's just, if you get really close to it, some weird stuff can happen. So if you have a black hole in the center of a galaxy, it will just orbit. And then as the galaxy gets shredded, it will be the last thing disrupted because it's at the center of the object. So it's most strongly bound. And it would probably just end up in orbit around the Milky Way. Yeah. If that galaxy has a black hole, which most dwarf galaxies don't show evidence for. Okay. And then there are my favorite objects that happen when you have an interaction between a big galaxy and a little galaxy. If you are lucky enough that the little galaxy plunges right through the disk. And so instead of nicely orbiting out at some large radius, it goes right through the middle of the spiral galaxy. You can get something like this. So this is called the cartwheel galaxy. This is, again, a multi-wavelength view combining imaging from all different space observatories. But this little galaxy went right through the middle of this big one. It punched right through the disk, causing a wave of material to move outwards, a density wave that created a dense region in a ring and a burst of star formation in that ring. So this is a whole bunch of star formation in a ring at a large distance from the center of this galaxy. And it's not the only one. There's another one. So these galaxies interactions between what is a pretty small galaxy can have a big impact on a large galaxy, but it depends on exactly their interaction, what the orbits are like. Okay. So the other thing I want to talk about today is not just mergers between galaxies, but the impact that the overall environment has on a galaxy. So where galaxies live will impact their evolution. And so you can roughly categorize the environments of galaxies as being isolated, sometimes called field galaxies, no big nearby neighbors. These tend to be star forming, mostly spiral galaxies. You can have small groups of galaxies, as small as the local group, Milky Way and Andromeda and our satellites, up to collections of tens of biggish galaxies. And then you can have rich galaxy clusters, which have upwards of 1,000 galaxies, all gravitationally bound to each other. And what you can see right away in this picture is that galaxy clusters are primarily made up of elliptical galaxies. Lots of, this particular one for sure, lots of orange fuzzy blobs here. This is an interacting galaxy. You can see a tidal tail here. Groups are made up of a diverse collection of galaxies. Some of them look like little mini clusters. Some of them, the populations look more like the field, like isolated galaxies. So this has long been my favorite regime in which to study galaxy evolution. It's the place where a lot of action happens. So if, as the universe evolves, we primarily go from having lots of spiral galaxies to having more ellipticals, and clusters already have lots of ellipticals, then it's this intermediate environment where I think a lot of that evolution happens, where you go from being spirally to elliptically. So more mergers, more interactions actually happen in the group regime, not in the final end product, which are clusters, as we'll see. So I think groups are the most interesting place to study galaxy evolution. I also think they're the hardest place to study galaxy evolution. So if I show you a picture of the night sky and there's a galaxy in it, great, you know there's a galaxy. If I show you a picture like this is a deep field image from a survey from the Canada, France, Hawaii telescope. Nice multi-wavelength image here. It's all optical filters. There's a whole lot of galaxies here. You can't tell me where the groups are. So I think groups are really, really interesting, but they're hard to study. So this previous slide, if you saw a picture that looked like this, whole bunch of orange fuzzy galaxies really close together in the sky, you have a galaxy cluster. Galaxies you can see. Galaxy groups are hard to see because they don't stand out in a field like this. So how do I know I have a galaxy group here? I have to go and measure the distances to every galaxy and find collections, small collections of galaxies, which are all at the same distance. So an image is not enough. A picture is not enough to find a galaxy group. It's good enough to find a galaxy. It works to find, if you have a color image and you can find all these orange fuzzy blobs, it's good enough to find a cluster. But for groups, we need to do something more. We need to find the distances to all the galaxies. And just to note another reason why I think groups are so interesting, we just talked about mergers. In order to have strong interactions, you want to have galaxies close together. You might think that galaxy clusters with 1,000 galaxies would be the best place to see galaxy interactions. However, how fast galaxies move has to do with how much gravity is there. And a galaxy cluster is so big, has so much gravity, the galaxies are flying by each other at 1,000 kilometers per second, and they hardly interact. So they just fly by each other. They never merge. A galaxy group, the relative motions of the galaxies are actually comparable to the speeds at which they rotate. So the Milky Way, for example, rotates at 220 kilometers per second. That's about the speed of a galaxy in a group. And when you have the speed of the galaxies comparable to the speed of their rotation, they interact really, really strongly, and you get more mergers. So the group environment is an awesome place to study mergers. Okay, so picture's not enough. You have to measure distances. We use a tried and true method to do this. So Edwin Hubble showed us way back in 1929, and now we actually don't call it Hubble's law, which is what I learned. We call it the Hubble-Lemaitre law, recognizing that it was not a lone contribution to astronomy. There were actually other people, and Lemaitre in particular, doing the same kinds of measurements at the same time. But what we do is we use this method of measuring the redshift of light from spectroscopy. So we can't just take a picture, we have to take a spectrum of each galaxy and measure how much the light is redshifted. Every galaxy, the light is redshifted, but the more it's redshifted, the further away the galaxy is, the faster it's moving away from us, is what we learned from Edwin Hubble. The universe is expanding, everything's moving away. The faster it's moving away, the further away the object is. And so if a bunch of galaxies are at the same distance, they'll have the same redshift. So if you see a few galaxies close together on the sky, they all have the same redshift, that's a galaxy group. So just to show a real example of this, here's a project. This is an image from the Canada-France-Hawaii telescope. And I went and got redshifts for a bunch of the galaxies in this field. And it's probably hard to see in the green font, but these are the redshifts of all the different galaxies. And within this yellow circle, there are 3 galaxies that have redshifts that are consistent, which tells me I have at least 3 massive galaxies that are close together on the sky and close together along the line of sight in redshift. And so this is a galaxy group 2 billion light years away. So that's one little patch of sky. There's a slightly bigger field of view, the same image, the same patch of the sky where I would see a bunch of galaxies. I'll have a whole bunch of groups all at different distances and therefore different redshifts. So it's a more observationally expensive thing to do to find groups because you have to measure all these redshifts, all these distances. But once you've done that, you have this nice sample of lots of groups, sometimes some clusters, and you know the distances to all your galaxies. Okay, so I think I'm going to skip a few slides. All right, so there's a whole bunch of things that are unique to living in a group or a cluster. You can imagine if you're a galaxy all by yourself in the universe, your evolution is mostly dictated by local things. Do I have a black hole in the middle of my galaxy? And how active is it? How much gas do I have? How much star formation do I have? But it's on most timescales, everything is self-contained. So it's all internal to the galaxy. That's what's dictating its evolution. If now you take this galaxy and you dump it inside of a group or a cluster, there's a whole bunch of extra stuff that can happen. You're moving through a huge dark matter halo as you orbit the group or the cluster. You have nearby neighbors you might be interacting with. There's a whole bunch of processes which happen in these dense environments, which don't happen to galaxies living all on their own. And so here's just 5 of these processes. I'm going to talk about one, show you examples of one, but the top 3 are all what I would call gravitational interactions between galaxies. So harassment is like the thing that made the cartwheel galaxy. So it's an interaction which it's not a merger, it's a fast interaction or an impulsive interaction, but not an actual merger. Then we have mergers. We also you can have during the mergers and also even in flybys, you can have tidal interactions, which stretch out material and strip it off at large radii. So that often strips away the outside parts of galaxies. And then we have the bottom 2, which are hydrodynamic interactions. So the top 3 are gravity. The bottom 2 are hydrodynamic, which basically just means they have to do with the gas physics rather than just simply gravity. And I want to talk about ram pressure stripping today. That's what I want to finish with because that's one of the things we're working on right now in my research group and we're most excited about. So ram pressure stripping is a process that happens when a galaxy falls into a group or a cluster. So let's imagine I have a nice cluster of galaxies here, and I have a little galaxy that's outside, but it's feeling the gravity, it's close enough in the universe, and it falls in, it's accreted into this galaxy cluster. Now what happens as this galaxy, which has its own dark matter halo, falls into this group? It feels a wind from moving through the galaxy cluster. So one thing that you may not know about galaxy clusters, and you shouldn't, and I should have told you, is that not only do you have galaxies, they all live in one big dark matter halo. And within that dark matter halo, there's also some hot gas. And we know that because we can see it with an X-ray telescope. And I'll show you a picture of that in just a minute. So you've got a whole bunch of hot gas, a bunch of galaxies, and here we have a galaxy falling in. This galaxy will feel a wind. It moves at a pretty high speed as it falls in. There's a lot of gravity there, so it's falling in at a high speed. It feels a wind. And when that happens, here's a real picture of a galaxy falling into a galaxy cluster. This is a galaxy in the nearby cluster of galaxies you may be familiar with called Virgo. So the Virgo galaxy cluster. The grayscale image in the background is a red filter image. So it's showing us the starlight from this galaxy. And the center of the galaxy cluster, the Virgo cluster, is in the direction of the lower left-hand corner. So this galaxy is moving towards the lower left-hand corner. And the contours are hydrogen gas in this galaxy. So the gas, which is collisional, is feeling this wind as it is moving through the cluster. And the gas is being stripped out, blown out of the galaxy. So the faster this galaxy moves, the more dramatic this stripping effect can be. And so we've understood the physical process behind this for a long time. And now we finally have the observational capabilities to study this in a large number of groups and clusters at many different wavelengths. And so this is a slightly older result. And now we have a whole bunch of really dramatic cases of this. And the most dramatic ones we call jellyfish galaxies, which they do kind of look like jellyfish. So here on the left and on the right are two galaxies moving in the direction of the center of their cluster is with the red arrow. So that's the way they're moving. And what's shown in the blue on the right and in the reddish pink on the left is ionized gas. So this is H alpha emission. I know some of you have H alpha filters you like to use. This is H alpha emission. So it's ionized gas coming from star formation, primarily from gas that's being stripped out of these galaxies. So the galaxy is moving through the cluster and gas is being stripped out. And as it's being stripped out, it's not just like we see hydrogen gas that's neutral gas. We actually are seeing ionized gas, which tells us there's actually star formation happening outside of the main part of a galaxy. This is new. We hadn't seen this until very recently. So this is really exciting. So we have these jellyfish tentacles, and these are spectacular images of this. But my very, very, very favorite image of one of these dramatically stripped galaxies is this one. So this is real. This is a Hubble Space Telescope image in the background. And then this red emission is from narrowband H alpha imaging. So again, ionized gas taken from the Subaru telescope, which is an 8-meter class telescope on top of Mauna Kea. So this is ionized gas trailing behind this galaxy as it's flying through its cluster. It's dramatic. So these kinds of things don't happen to galaxies living in isolation. There are unique processes and unique things that happen to galaxies living in groups and clusters. And that's one of the things that we study in my research group. So one of the projects we're doing right now is using the Canada, France, Hawaii telescope to study some of these stripped galaxies. And just to show you the optical imaging side of this, this is a galaxy that's undergoing a little bit of stripping, not as dramatic as the picture we just saw, but this is a color filter, a color image on the right, which comes from combining a ultraviolet, a U-band image with a red R-band image, which is showing us the stars. So you can think about this as being star formation coming from ultraviolet and stars coming from starlight coming out in the red, and you combine them to make the image on the right, with an average to make our G color in between. These are images taken from on top of Mauna Kea, the Canada, France, Hawaii telescope. So I've been lucky enough to go observing there a bunch of times. And we are really lucky to have this telescope, which is now decades old. It's built in the 1970s, but it sits on top of Mauna Kea. So it has just amazing image quality. It's a 3.6 meter telescope, whereas the modern telescopes today are 8 and 10 meters. So it's a small telescope by that standard, but it is in the best observing site in the world. So that means we get these super high spatial resolution. You may have heard of the Sloan Digital Sky Survey before. That's biggest survey of the night sky ever done was done from New Mexico. And you can see the image quality difference, same filters here, between being in Hawaii and the seeing in Hawaii compared to being in New Mexico. So big difference. And if you really want to study detailed galaxy shapes, you'd rather be in Hawaii. I mean, you'd rather be in space, but Hubble only has so much observing time and it has a really small field of view. So for some science, we're really lucky to have the Canada-France-Hawaii telescope. So I'll just finish with late breaking news. So every year, different observatories have deadlines at different times where you get to propose to ask for telescope time to do your cool science. And tomorrow is the deadline for the ALMA Observatory, which is a radio telescope in Chile. And we're applying to observe 10 of these jellyfish galaxies in another nearby cluster called the Coma cluster. So the Coma cluster is also a northern sky cluster. It's the nearest very, very big galaxy cluster in the universe. So galaxy clusters come from a range of having a few hundred galaxies up to a few thousand galaxies. Coma is the nearest one of the really, really big clusters in the universe. And the fuzziness you see here, this is the X-ray emission from Space Observatory. And these little white boxes are 10 galaxies we have found with CFHT imaging that look like they're these stripped galaxies. And we also have some imaging from a radio telescope in the Netherlands called LOFAR, which is showing stripped gas behind them. So we're asking for ALMA observing time to study these in much more detail. So ALMA is a wonderful observatory with super high resolution that we can really study the properties of the gas in these tails, how much they're star forming, what's different about star formation happening in the tail of a jellyfish compared to within a galaxy, which is one of the science questions we're really interested in. So there's the 10 targets that we're proposing for. So wish us luck. The deadline's tomorrow. The oversubscription on this telescope is about 5 to 1. So you have about a 1 in 5 chance of getting your proposal accepted. So it's very nerve-wracking because you only get one chance a year to apply. So I'm happy to take any questions about any of this. I just kind of highlighted a few things about mergers, a little bit about galaxies and groups and clusters, but I feel really lucky to be working in this field right now. We've got these amazing observatories in space and also on Earth to enable us to do multi-wavelength studies. I think it's fun to imagine that although galaxy evolution is a slow process, interactions are common. Galaxies don't just form and stay the same forever. They are evolving due to internal things and external things. And the environment which I'm most excited about are galaxy groups, but they are particularly challenging for this problem of they don't stand out. You can't just take an image, you have to measure distances to every single galaxy. So I'm involved in some big projects to try to do huge spectroscopic surveys where we measure distances to many, many, many thousands of galaxies, not just nearby. A lot of that work has been done, but galaxies much further away when the universe was much younger and a lot more active actually than it is today. So we want to understand what galaxies were like in the past. So I'll stop there and I'm happy to take any questions.
Laura?
Yeah.
Back when galaxies merge, the gases collide and there's star forming.
Mm-hmm.
Is it possible that our Milky Way galaxy only produces 7 to 10 new stars each year?
The star formation rate of the Milky Way is about 1 star per year.
Okay,
So,
and the second question was our black hole. Are there stars that orbiting the Milky Way black hole that are close to half the speed of light?
yes, that is in fact the work that was awarded the Nobel Prize this year. So half the speed of light is a little bit high, but there are stars really close to the center of the Milky Way, which are orbiting at incredibly high speeds around the central black hole. Not half the speed of light, but at much, much, much faster speeds than we're orbiting out here at our location.
So giant stars bigger than our sun are whipping around the black hole at massive speeds.
Mm-hmm.
Unbelievable.
I mean, stars of all sizes. So big stars, small stars orbiting around the black hole really fast. And that's how your orbit tells you how much mass is between the center of the object, and you. So exactly the same principle we talked about before. I can measure the mass of the Milky Way by studying the orbits of globular clusters. So all the mass between the center of the galaxy and the globular cluster, I can measure by studying the orbit of a globular cluster. In the center of the Milky Way, if I find a star really, 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 really close to the center of the Milky Way, I can measure the mass of the black hole that it's orbiting around. If you find stars further away, it's harder to tell how much mass is the black hole and how much mass is everything else in the middle of the galaxy. So the critical work that Andrea Ghez and Reinhard Genzel did that awarded them the Nobel, for which they won the Nobel Prize this year, was finding those stars at the very center of the Milky Way and monitoring them over the last 2 decades and mapping out the orbits of these stars super close to the center of the Milky Way.
Thank you.
Yeah.
Going back to that topic, didn't they create a video, time lapse, demonstrating the motion of the stars relative to the position of where the black hole would be?
That's right. So because they took images because they monitor it regularly over years, you can turn that into an animated GIF, basically. So you put together all of your images and you actually see the star, the central position of the central star orbit around.
That's phenomenal.
Yeah. But the most exciting thing about that research, besides the science, which is amazing, that for me, the really amazing thing was also on the technical side. So I showed you tons of Hubble Space Telescope images tonight because those are the highest spatial resolution pictures we take. But there's actually another technique to get comparably high resolution images from the ground. It's called adaptive optics. And with adaptive optics, what you do is you monitor the atmosphere with lasers, and you have deformable mirrors, which you can actually change the shape of the mirror in real time to correct for the seeing of the atmosphere, the blurriness of the atmosphere. And so the 2 groups that won the Nobel Prize for their work on the black hole, that was the revolution that enabled the science. So you could not have seen those stars orbiting a black hole if you didn't have super high resolution and monitoring capabilities. And the way they did that was by setting up these adaptive optic systems. So it was really a technological leap that enabled the cool science.
Thank you.
Yeah.
Laura, how do you measure the direction of motion of a galaxy? How do you do it when it falls into a group?
Very good question. I only see it in projection. So what I mean by that is let's take this picture I have on the final slide of this little group of galaxies. I've got a few galaxies there. All I can measure is their motion towards me or away from me using redshift and blue shift. So compared to the center of the group, I can measure are they moving towards it or away from it. I actually can't measure the velocity in the other directions. Yeah, because it takes too long. Like that would take millions of years to be able to detect. So I can't see that, but I can measure the direction of these tails and infer their motion. But you are absolutely right. I cannot directly measure their full motions on the sky, only their motion towards me or away from me. And then I can see in projection in XY, in RA and DEC, where they are on the sky. But that's the only information I have, RA and DEC and velocity along the line of sight.
Okay.
So another question regarding direction. I know you have to make inferences, but are galaxies all moving in the same direction or not? Like counterclockwise, clockwise?
So
like up and down, but like which?
The rotation direction.
Yes.
Yeah, so we know based on the spiral arm pattern for spiral galaxies, which way they're moving. And also remember that each galaxy has a different inclination to us. So very, very few galaxies are directly face on, in which case I can't tell you much. But if they're at all inclined, then I can measure how much one side of the galaxy is going to be coming towards me and one's going to be going away from me. So one side will have a different redshift than the other side.
All galaxies move in different directions then? Like they move in oppositional directions?
So each galaxy
to each other, not relatively, but I mean, they move in any direction they want, right? It's random, chaos.
Not chaos. So each galaxy will have, like every spiral galaxy will have its own rotation direction, and we can measure that. But compared to us looking at it on the sky, each galaxy is its own thing and it has a random direction of motion. But we can measure within that galaxy how its motion, and that's not random. That's a nice rotation.
Thank you.
Yeah.
Laura, you were talking. I couldn't help but think about M82 and appearance. I don't know if it's a loaded question or not, but what are the mechanics involved there? Why does that galaxy appear to, is it being stripped of its hydrogen gas or being affected by M81, or what's going on there? It's
a star bursting little galaxy. So it is undergoing it's got a lot of dust. It's really bright in the infrared. It's undergoing right now a starburst, and I do not know the mechanism, but I would not be surprised. It's almost certainly due to interaction with M81. But I mostly study the faint fuzzy things that are a bit further away than M81 and M82. I always, when I talk to my colleagues in the department who study the really nearby galaxies, they know all the Messier numbers and all the NGCs of every nearby galaxy, and most of mine don't have labels that anybody would know. So the typical research I do would involve thousands of galaxies in a bunch of different groups and clusters at great distances. And so they don't have IDs or tags that are unique that anyone would recognize.
Thank you.
Yeah.
In regard to your imagery, your time, I'm curious to know what's the process you have for getting time on these telescopes?
Yeah, so we're really fortunate to be in Canada, where the National Research Council, as part of their mandate, is supposed to provide Canadians with access to observatories. So effectively what that means is that Canada is a partner in a few different world observatories. We can't do good astronomy from Canada, unfortunately. So for a very brief period of time, the largest telescope in the world was in Victoria. And if any of you have ever spent time in the Pacific Northwest, why would you ever build a telescope in Victoria? But anyway, most of the best observatories are in Chile and Hawaii, and we own part share in some of those telescopes. And for the ones that we are partners in, we get to apply either once a year or twice a year, depending on the telescope. So you write a proposal, which is asking for some telescope time to do some specific science. Let's say I want to study some galaxy cluster. I want to study it with 5 different filters, and I want to do some spectroscopy. I would apply very specifically for what I need to be done, how much observing time, how much calibration time I need. And I would write a very good science justification. I would have partners probably from different institutions on that proposal. I would submit it. It would be reviewed by a panel and also expert referees. And 4 months later, I would find out if I was successful or not. So you're always applying for things for next year.
Very good. Thank you very much.
Yeah.
And I enjoy your enthusiasm for your studies. It's nice to see that. Thank you.
Well, I get to study galaxies for a living. Pretty lucky.
I think there were some questions in the chat.
Unfortunately, I have managed to freeze my computer on. Yeah, I can't go to full screen, unfortunately.
Right.
So someone will have to read the chat questions to me if they're there.
Laura, I want to ask you one more question, and I'm not sure that this could be a little bit too much because it's more like a conclusion. In your years of observing, did you see more spirals or ellipticals? And if you can tell me by number and by mass, not just number. So by number, did you see more spirals or ellipticals? And when you account for the mass, is it by mass? Is it like more spirals or more ellipticals? Like from your experience, based on your experience.
So it's not just my experience. This is a well-answered question. So at high mass, so the most massive galaxies are predominantly ellipticals, which makes sense because they're the merger products. So if I go to the most massive galaxies, which have masses about 10 to 50 times more massive than the Milky Way, those galaxies are almost all ellipticals. If I go to the Milky Way, a little bit less massive, they're almost all spirals, and there's a crossover in between. So you go from low mass galaxies being mostly spirals, high mass galaxies being mostly ellipticals.
Okay.
And Laura, you said you were looking for two massive black holes to collide. When
Yeah.
Virgo is up and running right now, are they detecting small black holes every day colliding?
So they're sensitive to what are called stellar mass black holes. So we kind of have two regimes of black holes in the universe. You have stars that blow up as supernovae and leave behind a black hole. And that's what I would call a stellar mass black hole. It might be 10, 20, 30 times the mass of our sun, but it's, of order roughly the mass of our sun. Then we have huge black holes that live in the center of galaxies. And LIGO and Virgo are only sensitive, the frequencies they study are only sensitive at finding stellar mass black hole mergers. So we don't have an experiment running yet today that can detect the mergers of supermassive black holes. So the next generation experiments, that's what we're hoping they will find. So there's a proposal for one for space called LISA. So take the LIGO experiment, make it 1 million times bigger and put it in space. It's a pretty ambitious project, but some of the technology has actually been tested in smaller missions to make sure that it will work. So Virgo and LIGO can only detect the smaller black holes that merge, and it's not finding them every day, but it's finding them very frequently now. It's a revolution. So it's like a new window on the universe. Up until 2016, we've only studied the universe in light, and to a much lesser extent in neutrinos. We now have a whole new window on the universe. So not just particles, not just light, gravity, directly studying gravitational waves. It's amazing.
So the supermassive black holes you're looking for are not in a galaxy. They're just out in space by themselves?
No, they're in the center of galaxies. So let's picture Milky Way has a big black hole in the middle. Andromeda has a big black hole in the middle. And every big galaxy has that. When the galaxies merge, at the very end, these two black holes should merge in the middle. But we haven't detected that yet. Black holes don't give off light, so it can't see it with our light-based telescopes. We need to see it with gravitational waves, and we don't yet have an experiment sensitive to finding that kind of merger of black holes.
Dr. Parker, I'd like to ask one of the questions that was posted on the chat.
Great.
Raymond asked, how excited are you for the James Webb Space Telescope? That's the acronym was JWST. I think I got that right.
You did, James Webb Space Telescope, yeah.
And will you and your team have anything in mind to apply to?
Yes, absolutely. So the James Webb Space Telescope, many people call it the replacement of Hubble, but I think that's sort of underselling it a bit. So the Hubble Space Telescope is an optical telescope. It's 2.4 meters across. That's about as big a telescope as you can launch in a single rocket. James Webb will launch hopefully within the next year. James Webb is a 6.5 meter telescope, which is too big for any rocket. It's too big across, so it all will launch folded up. We'll get into space and unfold. But unlike Hubble, it's an infrared telescope. So it has a bunch of infrared instruments, which means it can see planets, which are bright in the infrared. So it's exciting to study planets. And for my research, it's really exciting for studying the most distant, the furthest away galaxies. So as galaxies get further away from us, the light gets more and more and more redshifted. So all the stuff that I study right now in the optical, if I go to the most distant galaxies in the universe, I can no longer see them with my optical telescope. All the light has been redshifted into the infrared, and you need a good infrared telescope. And that's what James Webb will be. So to start with, I'm excited about some of the surveys that are being done that we know are coming, that were part of the original proposal for some of the instruments. And then my team is absolutely planning to do some observations of very distant galaxy groups in the infrared with James Webb. So fingers crossed it launches properly and it manages to unfold and get itself all aligned and working in space. It's an incredible feat of technology. It's also been about $10 billion. So it better work, or else we're going to lose a lot of credibility.
Yeah.
As
Thank
Canadians, yeah, no problem. One other thing, as Canadians, we should be really excited though, because we have all used the Hubble Space Telescope. It's been wonderful, but Canada didn't directly build any of the instruments. Canada built one of the 4 science instruments on James Webb. So we actually are part owners of it in a way that we were not for Hubble. Super exciting.
That's cool. Thanks.
Yeah.
Laura, I have a question. So you mentioned some elliptical galaxy could turn into spiral galaxy if it is interacting with some other smaller maybe galaxies. So do you know if there is an example we can observe? Well-known example.
Example of, I'm sorry, could you repeat?
Yeah. Is there an example galaxy we can find and take a look, which was could be believed that what it used to be an elliptical galaxy turned into a spiral one?
Yes. Okay. So
yeah.
this was the thing I mentioned, that you take two spirals, you merge them, you make an elliptical. If you leave it alone long enough, you can maybe grow a new spiral around you. We actually think that that is probably quite common. So you may know that galaxies, when I showed you that Hubble tuning fork diagram, and I've frozen my, I have some access again. Okay, good. One of the things on the Hubble tuning fork, as you go from left to right, we go from three-dimensional to diskier and diskier. These galaxies labeled SA.
I see.
In the middle, they have a pretty big bulge. So I made it very simple. I said you've got three-dimensional on the left and you've got frisbees on the right. But there's actually kind of an in-between zone where galaxies have a disk, but they have a big central concentration called a bulge. And we think that quite a few of the galaxies around us in the universe today that look like that, the bulge might have grown from a merger a long time ago. And then the galaxy grew a new disk.
Oh, I see. Yeah. Awesome. Thank you.
No problem.
The Sombrero galaxy, is that, it has a huge bump in the middle. Is that, would that be one of those?
It could be. I mean, this is one of those things where when you see the very final product billions of years later, you're doing an archaeological dig and you're trying to understand where, from the stars we see today, what must have happened billions of years ago. So it's difficult, but for sure, we have a bunch of galaxies that have very big bulges, and this would be a natural explanation for them. And in simulations, it seems to work well to reproduce what we see. But for an individual galaxy, it's hard to say exactly what its past was a long time ago, but this is likely quite a common pathway, we think.
We have other questions? No? Well, thank you, Laura. This is amazing. I mean, so much information. I can't even handle it all, basically. But it's really, 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 really educational. I'm sure everyone appreciated them. Everybody liked it?
Thank you very much, Laura. Dr. Parker.
My pleasure.
Thank you, Laura.
Yeah, thank you.
Thank you.
Thank you.
Gives us a great idea of how what the depth of research is these days that we don't often hear about. Thank you.
Yeah, it's true. I had no idea of some of the research that's happening. And we had a good talk about, what was the last one? Oh, I can't remember. It was very informative also. Some of the research going on is pretty amazing how these instruments are being utilized. And yeah, our little ground-based astrophotos that we do here, but it gives a whole new perspective on actually what's going on with them. And it kind of raises the bar. Anyone else have any other questions?
I've got a question. Earlier in your presentation, Laura, you showed us a galaxy that was formed about 3 billion years after the beginning of the universe. So it would be roughly 11 billion years distance, light years distance. And you talked about galaxies being redshifted. Are there galaxies that have been so redshifted or so far out that we can't or will never be able to see them?
So the universe is 14 billion years old, as you mentioned, and with the Hubble Space Telescope, we can see back to about that limit that I showed with that galaxy. James Webb will let us see back even further, and we should be able to see the first galaxies. So the thing we know about the universe is it started a finite time ago. So it's not like the universe began and poof, there were galaxies. The universe began and it was a sea of elementary particles, and it took 300 to 500 million years, depending on your favorite model, for the first galaxies to form. And the wavelength sensitivity of James Webb should enable us to see back in time that far. So we expect with the James Webb Space Telescope to see the very first galaxies that formed after the Big Bang.
So we'd be seeing literally to the center of the universe.
Alas, there is no center of the universe.
But everything Big Banged and exploded outwards, so it had to Big Bang somewhere.
Unfortunately not. So the universe is a cruel, cruel thing. So the Big Bang makes you picture an explosion, but the Big Bang is a description of the beginning of the universe. It happened everywhere at once. So there need not be an edge nor a center. And this is one of the hardest concepts I teach. But the universe has been expanding from every point for 14 billion years. There is no preferred location. So from our perspective, every galaxy is moving away from us. Hubble saw that in 1929. So he measured redshifts, every galaxy is moving away. If you could transport yourself to some other spot in the universe, everything would be moving away from you. So everything's been moving away from everything else for 14 billion years. There's no preferred location. There's no center.
So we could literally see things that are like possibly 20 billion years away then.
No, we can only see back we can only see back in time for the finite age of the universe. We can't see anything from before that.
So I'm just trying to wrap my head around this, because if everything is expanding from its own direction, and you're at one whole other area of expansion and trying to see the whole other side of expansion, and they're expanding at the same time conceptually, possibly you could be seeing things that are way further than the beginning of the universe.
I think a better way to picture it is there are things beyond which you'll never be able to see. So our observable part of the universe, where there's been time for light to reach us, is not the entire universe. So the whole universe is bigger than the part we can see, because those other places out there, which have had their own expansion this whole time, are beyond our observable universe.
Currently.
And then as our universe expands, their part of the universe expands. And so it depends on the expansion rate, whether you'll see more over time or not.
Or the type of tool that we use to see. Right?
No, because light just gets redshifted by a known amount. So the expansion and redshift are the same thing. And
but
we have
seeing the dark as well, right? Like what if we just get away from seeing the light and we go into seeing the dark, or seeing magnetic fields, or seeing, other things that maybe we could see further?
Everything moves at the speed of light or slower. So the best we can do is use light, and light comes in every wavelength. So if you can't see in the optical, look in the infrared. If you can't see in the infrared, look in the radio. You always have a wavelength of light to look at, and you'll never do better than light. Nothing moves faster than the speed of light.
That we've discovered so far.
It would break a whole bunch of laws of physics, which are very well tested.
Yeah.
So yeah. No evidence of anything moving faster than the speed of light, or else you'd be able to also have time travel, which I think most of us expect doesn't happen.
Thank you.
Yeah.
All right.
And if you know anyone who goes to McMaster, I teach a general level class on all these kind of big questions. You can take it if you're a science student, but it's available to everybody. There's no math. So I teach a concept level class at McMaster. So
okay. I had only taken intro level astronomies at Laurentian way back when, then did psychophysics, and then moved into psychology, social psychology, but the very similar principles apply conceptually. So if it's a conceptual thing, then that's something I'd like to explore, philosophical, conceptual possibilities. Really, I'm talking new ways of thinking outside the box.
Yeah, well, I teach it from my astronomer, astrophysicist perspective, but yeah. What I meant by conceptual was that we teach it qualitatively rather than, I also teach advanced, graduate classes where it's all math, but that's not for everybody. It's nice to have a class where you can talk about the Big Bang and black holes and all those cool things you've learned about without being bogged down necessarily in the math. Those courses exist, but this is a class without the math. So if you know students at McMaster that would like to take such a course, recommend it. Also, if you have friends who live in Hamilton, I like having mature students in class too. It's fun.
But what if the Big Bang never happened and we have just particles that existed out there, like protons and electrons that existed out there, and we have other mechanisms that produce this expansion of the universe? Could that be an alternate?
Yeah, so the simplest explanation for every observation that we have so far is that the universe started out very hot and dense 14 billion years ago. So if the universe started out hot and dense 14 billion years ago, there's a bunch of predictions you can make. What you would have for particles, that the universe would be expanding, that you would have cosmic background light, which I didn't get to talk about today, but it's something else we observe, that you would have the number of atoms of different kinds that we have in the universe. There's a whole bunch of predictions you can make. All of those predictions are predicted by the Big Bang model and not by any alternative we have right now. So the only theory we have that explains all current observations is the universe started out very small, very hot, very dense, 14 billion years ago.
Will the universe blink out one day?
Will the universe, pardon?
Blink out one day?
What does blink out
mean? Just expend its energy and go dark.
So the future of the universe, I actually offered, the person who invited me to come tonight, I offered 2 possible talks, one on galaxies and one on dark matter and dark energy. So if you want to have me back next year, I could come talk about the other topic. But one of the hottest topics in modern astrophysics is understanding this stuff called dark energy, which is causing the expansion of the universe not just to expand, but for the expansion to accelerate. So the universe is getting bigger faster, which is counterintuitive for a universe filled of stuff with gravity. You would expect expansion to slow down. It's speeding up. And the exact rate that it's speeding up is going to dictate what our distant future looks like. So that is a very hot, very open area of research. If our current measurements converge on what they're looking at, it looks like over time, the universe is going to expand at this accelerated rate, and the number of galaxies we see in the night sky is going to become fewer. The galaxies are actually going to expand out of our observable universe, and we're going to see fewer and fewer and fewer things over time. And if you're an astronomer 100 billion years from now, and you live in a galaxy called the Milky Way, you would only see your own galaxy. You wouldn't see distant galaxies, and that is bizarre. And eventually the galaxy you live in would use up all the gas it has. It would stop forming stars. Everything would cool off and die a slow, sad death. So that's what looks like the future is. So we should all be very happy that although these are difficult times, we live 14 billion years after the Big Bang and not 100 billion years after the Big Bang.
Even with COVID, this is a better time to live as an amateur astronomer.
Absolutely.
Yeah.
Saying that in galaxy groups, like for example, the Virgo cluster, most of the galaxies are moving towards each other and will merge, and the groups themselves are moving away from the other groups due to the expansion of the universe.
So first point, a slight clarification. Some galaxies will merge, but lots of them are moving too fast and will never merge. So it's not like all the galaxies in a cluster are going to end up in all merging together. You get some mergers and some galaxies just happily orbit around in that cluster forever. And then the other question was about between groups or between clusters. And once 2 groups or clusters are far enough apart from each other, then expansion dominates and they will never merge. So as the universe has evolved, in the past, groups and clusters used to merge pretty often. And actually, groups merging together is how we got the Virgo cluster in the first place. So Virgo actually has, we can still see by the motions of the galaxies that there's kind of 2 centers to Virgo. So it formed by 2 groups merging. But as the universe evolves and expansion is getting more and more dramatic, that's going to happen less and less often. So the clusters that exist in the universe today, that's probably the peak in structure formation in our universe. We're not going to make new, bigger clusters 10 billion years from now. We've kind of like maxed out the growth of structure.
Laura, with your research or group or some of the colleagues you work with, are there collaborations between amateur and professional astronomers?
Not directly in my field. In some areas, more in stellar astrophysics. So in the fields of variable stars and supernovae, there's collaboration. Not so much in my field, not in galaxies. The one place where non-professional astronomers are involved is not amateur astronomers, but citizen science projects. So there are some projects that take advantage of the fact that there are thousands of people in the public who are interested in astronomy. So for example, classifying images. So we now have some observatories that do, automatic surveys of huge swaths of the sky constantly. And you can write algorithms to look at the images. But there are some times that a human eye, and you probably all know this, you find weird things in your images. And so it's actually nice to have a human with a brain look at them, and in case your algorithm didn't think about something in advance. And so there are some projects that take advantage of interested amateurs. So the most famous one of those is something called Galaxy Zoo, which started by measuring the shapes of galaxies, but has been advanced over the years to look at simulations, to look at mergers, to look at all different kinds of images of galaxies to classify different things. Do you see a bar? Do you see spiral arms? How many spiral arms? And then that information, it's not like one amateur looks at the image. You've got thousands of people who look at all the different images, and then you can build up what we call a probability distribution for each galaxy. So what's the probability it has a bar is based on how many members of the public said it has a bar. And that statistical information is used in research papers. So Galaxy Zoo is a really nice place where interested citizens can contribute to real scientific research that ends up in papers.
Thank you.
Yeah.
A final question. If the universe is a three-dimensional object, what shape is it?
Great question. So what we measure is we can measure the overall geometry of the universe, and the most powerful tool to do that is using something called the cosmic microwave background, because that's kind of it's relic light from just after the Big Bang. It's the furthest away we can see. So it's the best to measure the large scale shape of the universe. And all evidence is that the overall geometry of our universe is what we call flat, which when we picture flat, we picture two-dimensional, but flat in 3D just means that. So I've got two parallel lines today, two lasers, and I shoot them out into space. They never converge, they never diverge, they stay parallel. So the geometry of our universe appears Euclidean. So all of the trigonometry you learned in school applies, even on the very largest scales in the universe.
Sorry, my computer locked up. Did you have a shape that you gave us?
Just that it's Euclidean. It's flat. Yeah,
Because I heard that they figured it was egg shaped.
It's not easy to picture what a three-dimensional space looks like, but it is the best description from a geometry perspective is that it's Euclidean. Parallel lines, they're always parallel. Triangles always have 180 degrees, not like we live on a sphere or on a saddle, but we live in a flat space, three-dimensionally. And again, I teach that in my class with pictures.
Oh, man. Well, thanks again. I think we've used up our time, and we've asked you lots of questions and got lots of information. And I think we should close our meeting at this point. And
I'll answer the last little question I just saw there in the chat. So the question about infrared imaging. Longer wavelength imaging, but much bigger telescope means James Webb will give us similar image quality to Hubble, but in the infrared. So whoever asked that question. So it'll be images as beautiful as what I showed you tonight from Hubble, but at infrared wavelengths. So it'll be super, super cool.
It's really interesting that we only see a small section of visible light, but there's all these other wavelengths that are all part of it. And to study in those wavelengths gives a whole different picture of everything. I mean, it's beyond our little tiny window of visible light that we get to see. Basically, that's very narrow, right? Talk about narrow band imaging.
Yeah, and on top of the full electromagnetic spectrum, we got neutrinos. We were able to image the sun in neutrinos, using neutrinos, not light.
Mm-hmm.
And then we have gravity, which is as good as probe as light for instance, dark matter. So we do have other tools other than electromagnetic radiation, which is amazing. So, but it's all based on the advancements in physics, because it's all physics in the end, isn't it? Astronomy, chemistry, everything is based on physics, and we depend on physics. And if we discover other things in physics, then that's going to help us to use it in astronomy. So
yeah, I mean, fundamental science is what leads to all of this, but you would not want me to build your telescope. We need engineers to actualize.
For sure. Yes. Yes.
Right.
Yeah.
Okay, thank you. Was there anything else? We really appreciate your talk, Laura, and we'll consider having you back on your next topic, maybe in the fall sometime.
Oh, yeah, please.
Yeah.
That would be great.
I'd be happy to give a talk on the cosmology side as well. That would be great.
That would be great.
Nice to meet you all.
Very enlightening. Thank you.
Thank you very much.
Thank you.
Bye.
Thank you.
Bye.
Bye.